the Soil Conservation Conference. The
I
convention.
would imagine the same thing, Dale.
Yeah, so it runs everything a little bit tight, especially for me if I travel that far.
Yeah, I think we want to alleviate those conflicts if we can.
Yeah, okay, I appreciate that. Thank you.
Okay. Hey, Dale, just so you know, there's already three Brians.
We have a quorum.
Yeah, I know the bunch of Brians out there.
Yeah, there's three Brians, the good, the bad, and the ugly, and I'm the latter, of course. But
you're the one that finally will survive.
Okay, Dean, you have a quorum, and it's the appointed time.
All right. Let me bring my stuff up here. We're going to call the meeting to order here today. And this will be Aquifer Stabilization Committee meeting number 4-26, Wednesday, August 26th, 9 a.m. Mountain Time, held at the Water Center and on YouTube and Zoom. So I guess we'll start out. Mylene, could you do a little roll call on the committee and board members?
Good morning. Mr. Barker?
Here.
Mr. Olmstead?
Here.
Mr. McMahon?
Here.
And also joining us is board members Cole-Hansen, Mr. Gibbs, Mr. Raybould, and Mr. Vanstone.
Okay, thank you. I guess we'll start out with our ESPA storage. And is Mike doing that one?
Yes, Mike is sitting right here in front of me, and he will start the presentation in just a second here.
Okay.
Thank you.
Yeah, go ahead, Mike.
Okay, good morning, everybody. My name is Mike McVeigh. I work in the groundwater modeling group here at IDWR in the state office. And as Dean said, we're going to talk about storage changes in the Eastern Snake Plain Aquifer. I'm sure most people have heard this presentation, and I'm definitely sure most people know where we're at. But I do like to show this. I think it's important for everybody to stay on the same page. And also, when you're presenting data, I think you need to have perspective and you need to know the story. And so the last thing I want is for you to think about where we're at. So during this presentation, you're going to see, there's no pointer. You're going to see this figure a lot. This is ESPAM 2.2 model boundary. And I just want you to get oriented. If you get lost and want to ask about a specific area, we'll figure out where we're at together. So we're talking about basically the aquifer water balance. Inflow minus outflow equals change in storage. However, that's a pretty deceptive equation because those inflows and those outflows are pretty difficult to come by. And we actually do spend a lot of time and money and effort trying to get at those. But at the end of the day, it just takes too long. So if you want to use storage changes to assess aquifer health or to assess the impacts of management, we need something more efficient. Unfortunately, we can cut directly to the chase by looking at water level changes. Because if you think about it, if there's more water in the wells, there's more water in the aquifer, less water in the wells, less water in the aquifer. And so that's the relationship that I leverage here. The process of calculating this is pretty simple. I just difference the water levels last year to this year, and then I interpolate those water level changes across the ESPAM 2.2 model boundary. So that gives me a volume, right? I've got depth of change, I've got the area of the model, but that volume also includes the aquifer matrix. It doesn't know that there's an aquifer down there. So to take care of that, I have to introduce this term specific yield. You've probably already read it, but my picture is better. That brown area is the unsaturated zone below your feet. Below that's the saturated aquifer. And the upper right is just this imaginary chunk of that aquifer. You hold it up in the air, a certain amount of water is going to drain by gravity. That's the water that's available to us. That's what we call specific yield. I express that as a percent, and I multiply that by that volume that I calculated earlier. That effectively removes the aquifer matrix and leaves us with a change in volume of water. So that's the calculation in a nutshell. It's pretty straightforward. Now, as you might expect, we need a lot of data. I'm doing an interpolation. And if you're not familiar, interpolation is just a way to estimate information where you don't have any. So you might expect on the right, you have 10, on the left, you have 0. Somewhere in the middle is going to be 5. And that's a simple type of interpolation. And so to reduce uncertainty, we want a large spread of a lot of wells. We want them fairly evenly spaced so we're not interpolating over large unknown distances. And so to do this, I started this kind of on a lark in my office. I grabbed what we call synoptic measurements or mass measurements. It's where we go out in the spring and we collect as many water levels in as short a time as possible because we're looking for a snapshot in time. And then I'm going to compare those snapshots year to year to year, and that's how I calculate the changes. So as part of ESPAM calibration, we conducted these mass measurements in 1980, 2001, 2002, 2008. And after 2008, we do them every 5 years. So 13, 18, and 23. And so we base those calculations on that because that was my biggest number of wells. Okay, so I mentioned that we conduct this in the spring. We do that for a couple of reasons. Because if you think about what we're doing, is we're trying to integrate the impacts of last year's irrigation activities for the most part. And so that takes time for that to settle down, basically. If you're in a groundwater irrigated area, those water levels are depressed. They need to recover to some static condition. If you're in a surface water irrigated area, they need to recede back to that same static condition. So we wait as long as we possibly can, but we have to take those next measurements before the irrigation season starts the next year, because I really want to avoid short-term or local impacts to those water levels. And so here's kind of a good example of that. You can imagine you go out and turn on your well for the first time. Water levels are going to tank in that well, even though you may have only removed a few gallons. However, if I go and I take that water level when you had turned on that well and compare it to last year's water level, it's going to look like there's a big decline in aquifer water levels. And I'm going to interpolate acre feet of change instead of gallons of change. And so that's something I really want to avoid. And that brings up this question of managed recharge, because managed recharge has this locality to it, either a well or a pond, something that we're putting water in a direct location. But it is also an intended change to the aquifer budget. And so we do need to capture that in some way. The trick is not to over count it by treating it kind of like one of these local or short-term water level changes. And so the way I do that to try to keep us safe is, there is no rule, there is no equation that can tell me how far away I need to be to not overcount managed recharge. So I looked at ESPAM. We discretized spatially by 1 mile grid cells. We discretized temporally, 1 month stress periods. And so that's what I use. Any well that's within 1 mile of a known recharge location, I don't use them. For wells that are located further than a mile, if I can see a recharge event in the data, then I make sure that any data that I collect must be at least 30 days beyond that recharge event. And that way I kind of capture the recharge, but I don't over accentuate it. And so that brings up transducers. A transducer, if you don't know, is just measures pressure. We put them in the well. We correlate those pressures to water levels. And so as water levels change, the pressure changes. That data is stored there in that transducer, and we come out and we download it every once in a while. Now, main thing is we collect a lot more data. And that data helps me in a few ways. One, it helps me understand well behavior. I understand what's going on in that well over time. It helps me pick more appropriate water levels. It helps us measure when we can't get out there. Remember, this calculation occurs with springtime water levels. And there are a lot of areas where we just can't get to them at the right time of year. But with the transducers, we're collecting those water levels at the right time. We just have to use them later in the year. And then finally, it really helps me with recharge. It helps me pick at least 30 days away from the known recharge. So this right here is a hydrograph from a well near milepost 31. I don't use this well because it is within a mile of the recharge location, but it's exaggerated, so it helps me make my point. So you can see my theory of coming in at the beginning of, right before the beginning of irrigation season. You can see it works really well. Beginning of April, beginning of April, beginning of April. But we get to 2015, this group started dabbling in managed recharge. And by the time we get to 16 and 17, managed recharge is something serious, and you can see its impact on the water levels. So now if I tried to come in with my old process of just picking a water level right before irrigation season, I'm going to make some pretty big mistakes. By having transducers, I can look this data and see what's the best date to pick, or if I can't pick any dates in this area. And personally, it's emotionally taxing to lose data, so I don't like that. Oops. I think we've got the wrong map. Oh, shoot. Okay, so let's look at some of those mass measurements. What we're gonna see this figure a lot. They're all gonna be the same, as in I have the years of comparison at the top, 1980 to 2001 in this case. The calculated volume change right here in the mid left. The number of wells for interpolation down here at the bottom. These black dots are those wells. This is the interpolated water level change that you're looking at. And then on the left, the color ramp for all of these is the same ramp. So even if you see different numbers over here, the colors are the same. You can just look at these figures and see if water levels are going up and down from comparison to comparison. So 1980, 2001, I calculated 2 million acre feet loss. I did this kind of on a lark in my office. I'm all excited. I show my boss, I show a couple of decision makers like Brian. They're kind of shocked. Everybody knew water levels were going down. That's something we've been dealing with for a long time, but to put a volumetric number on and one that's so large, I think took people aback a little bit. Okay, Mike, go back and do it again. 80 to 2002. This is freaky, right? 2 million acre feet in 20 years, 1.9 million acre feet in 1 year. So decision makers aren't any happier with me. It's getting a little nervous. Go back and do it again, Mike. 2008, we're down 6 million acre feet. Just giving bad news, always uncomfortable. 80 to 13, 7.5 million acre feet. And then 80 to 18, we've crawled out of this abyss into a really deep hole. And remember, we had Snowmageddon in between here, so there's reasons for this to have occurred. But nonetheless, I'm just showing a lot of bad news. By the time we get to 2023, we lost 9.3 million acre feet from the aquifer. So again, people realize what was happening, but I'm putting volumetric numbers on this. They're important and they're helpful, but they're also a little bit scary. So to me, like I said before, you need to have perspective, you need to have a story. And what I've done is just given bad news that's floating out in space, and it's really hard to use. So let's see if we can do something different. What can we do between these large mass measurement events? Well, in fact, we measure hundreds of wells on the plain every year, just as part of long-term regional management. And what that means is you just kind of go out in the springtime sometime when you can get away from your desk, when it's easily accessible, and we just kind of keep an eye on it. Over time, we'll see if something's happening, but we're not asking a lot of this data. However, doing these storage changes, we're asking a lot more of our data. So since 2016, we now measure them on that same short time scale that we do the larger synoptic measurements. That way it helps us compare more apples to apples. So now let's look at those maps. Same as before, we're looking at the years up top, comparison, calculated volume here on the left, number of wells, black dots are those wells, and these color ramps, or these figures, the color ramp is consistent. So again, you can just watch. As you're going through, you're gonna see a lot of shapes in here. I want you to keep in mind, this is the Milner-Gooding, a lot of managed recharge there. Southwest Irrigation District is doing injection. And then also notice down here at the far south of Oakley Fan, they piped a canal down there, basically shutting off the recharge. It kind of gives you an indication of what efficiency may or may not do for you. So 2015 to 16, minus 300,000 acre feet, not good, but at that time, that was kind of on average. We were averaging about 280,000 acre feet lost as an annual average. So I guess not surprising, not good, but not surprising. 16 to 17, this is Snowmageddon year. Now, this is the first time I'd shown anybody outside my desk a positive number. I'm pretty excited. I'm kind of buoyed as I go into the meeting, and people were a little dismayed. And I think what the issue was is relative to what I'd shown in those earlier years, 1.9 million acre feet lost in 1 year. This seemed small. We had Snowmageddon, more snow than anybody can remember. Why is it so small? Well, let's go to the next year. Maybe let me describe this here. If you look in the middle of the plain, you look at the northeast section of the plain, it's still pink. And basically all that heavy winter was still frozen. All that water is entrained in ice and snow and has not been introduced to the aquifer. So we go to 17, 18, things have melted. They've gone into the aquifer. Now we can see the total impact of that wet winter plus all of our management activities. So that brings up a good point. One, things do not happen on an annual time scale. We as people are forced to act on an annual time scale and assess on an annual time scale, but in fact, it kind of smears out a bit. Also look here, you can see managed recharge. It was early on, water rights were on for a long time. You can really see the impact of water levels from the board's managed recharge, see what's going down in SWID. And then also you can look at my little area down in Oakley. 18 to 19. I typically report to the nearest 100,000 acre feet. I think that's more appropriate. This is a high level look. It's hard for decision makers to go from negative 100,000, 0 to 100,000. So I do throw this in, I guess, for flavor. But at the time I said, this is kind of the ugly side of 0. And this is called a fairly good year. Then 19 to 20, 400,000 acre feet gain. That feels good. You see Oakley's still having issues. We can see a little bit of recharge. 2020 to 21. I know this story. 21 to 22, this is all too familiar. We're back down to those large annual losses. And I want to point out here what's going on Miller Gooding. You guys are still recharging, but it's less than it was in the previous years. These are all relative to the previous years. So if you put less water in, you're absolutely going to have a water level decline. But a way to think of that is without recharge that year, those declines would have been more excessive, right? They've been much larger. 22 to 23, again, million acre feet in 1 year. And then 23, 24, 800,000, again, we really like that. Notice also we're starting to get a lot of wells that were drilled, starting to come online. I'm able to use them, tighten up that uncertainty. 24, 25, calculated no change, and it was almost 0. That was very strange for me, but we can see recharge management actions are having different effects in different locations. And then finally, this year, 25 to 26, we lost 600,000 acre feet. I think I should pause here to see if everybody has any questions about this year's number.
Hey,
Okay.
hey, Mike,
Yes, sir.
this is Brian. Not really a question, but to me, it shows what a good reservoir that upper aquifer is. If we can, we can use it to store, up to a couple million in a year and have, real good impacts. That's
Mr.
all.
Olmstead.
Thanks.
Okay, thank you. Mr. Chairman, Mr. Olmstead, I agree. This is the best way for us to kind of even out the water supply. And I think you already know this. Not only can we impact storage, but it also impacts flow in the snake. And I'm going to show that here in a second. Before I do that, I do want do a little bookkeeping here. There are a lot of wells on INL, and I've always used, I get data from 112 wells that are not perched. These are all regional aquifers. I've always left them in there because that density doesn't improve or worsen the calculations. However, there are comments about this does beef up that number down on the right-hand side, maybe looks a little better than it should. So I thought maybe I should just go ahead and take care of that. So I went through and I removed 45 wells from that network. And those wells were almost all on INL facilities. And the way I did this choice is USGS has a water level monitoring network, and that's what I'm querying here. Those red wells that you see there were water quality wells. They measure water levels as part of that campaign. But this way, I'm just choosing what the USGS considers to be the best, most representative network for water levels. So if we look here on the map, this is what you've seen in the past with the removal. You can see what it looks like there. It's much more evenly spaced. It doesn't look so strange. So I think it's just better in several ways. But just so you know, I had already filtered out 5 wells for data issues. And so of those 45, I removed an additional 41. By doing so, I changed the estimate of storage change by 60 acre feet. And so I removed 11% of the wells and I got 0.01% change in my volume calculation. That's significant to me. So that's just a way to hopefully make you feel better for me leaving those in for so long.
So,
And we
Mike,
always like to look. Yes, please.
this is Al Barker. What's the net change between when we first started measuring, what was it, 81 to 26? What is that, 45 years?
Yeah, I've only calculated to 23 on that larger, but we can kind of add it up probably if we wanted to. I typically assess from 2015 till now as a kind of intermediate instead of those annual, just because that's when settlement activities and board managed recharge really took effect. If you want, I can send the group an email that calculates that 1980 to present, if that would be helpful for you.
I would be interested. I'm not sure how helpful it is, but I'd like to have a sense of what's happening over that long period of time.
Mr. Barker, I can do that easy.
Mr. Chairman, Mike,
Go ahead. You go ahead, Pat.
can you give us an idea of the amount of personnel and time involved in the mass measurement calculation?
Mr. McMahon, I'm not sure. Do you have an idea?
Would that be, is he asking maybe the 5-year or the year-to-year?
Yeah, I guess it is different. 5-year, we do engage USGS and others.
Yeah,
Craig Tesh is going to come up.
We can answer that question, Pat.
Hi, Pat. Mr. Chairman, Pat, this is Craig Tesh, Hydrology Section Manager. The 5-year mass measurement event is a pretty big event that involves a lot of staff from the USGS, and you know the amount of wells. It's 1,500 wells or so.
Almost 1,200.
1,200 wells. So it's a pretty big event that the board funds every 5 years. And year to year, I guess what's the exact question, Pat? The amount of staff?
I was just trying to capture the amount of personnel and time required to do the 5-year mass measurement event.
Yes, here at the state office, and we have about 20 staff from IDWR that participate in that event, along with, I don't know the amount of staff at the USGS, but it's quite a few. I would have to estimate probably 10 USGS staff. So it's a pretty good undertaking every 5 years, about 1,500 wells, about 20 to 30 staff. That's over one, 2 to 3 period. Yeah. Well, if that helps.
Thanks. Yeah.
Yep.
Okay, any other questions from committee members or board members?
Mr. Chairman, this is Jeff. Might be nice if we had a calculation of how the aquifer storage compares from 2015 to 2026, as well as Al's request for 1980 to 2026.
Yeah, I think that's a good idea, Jeff.
Thank you.
Thanks.
Okay, Mr. Chairman, Mr. Raybould, you're kind of stealing my thunder. We are going to show that in 2 slides here. I know there's an interest in showing the sentinel wells with these water level changes. And so there's the distribution. You kind of see how each section of the aquifer is responding. So here's, I was kind of saying we need perspective, we need a story, and this is that story. Again, I think a lot of people have seen that, but go through it, 1912 to 1980. The USGS did the aquifer water budget method, the N-out. And you can see that early on, water levels and storage in the aquifer really shot up. And if you think about it, you have these guys going out with horse-drawn wooden plows and sticks of dynamite trying to create these canals, scrape them out of the earth. And so they leaked quite a bit. And then they do this flood irrigation over large areas. And so you wind up with a lot of recharge over a large area over a long time. And it was really impactful. We get to the middle 50s, and a couple things happen. One, downhole pump technology made groundwater irrigation feasible. And 2, they started winter water savings, where instead of running water out onto the desert, they started storing in the aquifers. So we had a simultaneous increase in discharge and decrease in recharge. And the aquifer responded immediately. And so now you can see that we're pretty much just riding the weather down this long-term downward trend. And so that's kind of the story of what we're doing right now. Here's 2026, here's 2015, the second from the bottom right here. I guess I do have kind of a rhetorical question for members of this committee. And that is, it appears that we have a change in character here. And I just want to ask, you don't need to give me an answer, but do you think that we've changed it? Do you think we've stabilized things? And I'll give you a hint. I don't know. I only know equilibrium when I look backwards and see it, because we don't know what's going to happen next year. Was somebody asking a question?
No, you can't do that. Yeah.
Okay, and this the blue bars here, the calculated Thousand Springs discharge. I like to show this just because recharge does have more than one purpose. It stores water in the aquifer and bolsters flow in the Snake River. And so you can see here that as storage, as water levels go up, so does discharge to the Snake River. And as they've gone down over time, so is reach gains to the Snake River. This also happens in near Blackfoot to Neely, but I don't know as much about that reach. So Ethan Geisler is going to address that in his presentation. So here's Mr. Raybould, here's your map. From 2015 to 2026, minus 100,000 acre feet. I also add up my annuals and they also come up luckily to 100,000 acre feet. So that's a pretty good number over this time. And this last year put us in the negative. And showing the Sentinel well locations. So, I've mentioned a couple times about Snowmageddon, about management, aquifer management. Alex Moody will be coming up and giving a presentation. He'll kind of parse out maybe the reasons for water level changes in different areas. So to summarize, we lost 600,000 acre feet last year. And since 2015, we're down 100,000 acre feet. Then those last three bullets are just my raw statement. This aquifer does leak. We're going to have undulations in weather. And the only way this works is perseverance through the dry time. So try to keep the faith. Okay.
So
With that,
Mike,
I'll
this
entertain
is
questions.
Bob Barker again. So you have a number from 81 to 15, right? What the total is in one of your previous slides. So
81 to 13 and 81 to 18 or 80. Do you want to cruise to that?
No, that's all right.
Okay.
No, that's okay.
Okay.
Any other
All right, well, I will
questions?
get you.
Oh, sorry.
No, I was just going to wrap up. Let you know I'm going to send you out that change from 80 to 2026. If you have more questions, just email me or talk to Brian.
Okay, this is Dean Stevenson. I have one more question. It's probably a dumb question, but if you go back a couple of slides, it shows the big starting in like 1900 or somewhere around there where the number's pretty low on your kind of big, yeah, they're right in there. So around 1912, is that when how good a data do we have on volume? I mean, how do they extrapolate that? Because there wasn't a lot of wells and there's everything else. Is there some big data gaps in there? How do they figure that out, I guess?
Mr. Stevenson, USGS did this and they didn't use wells. We didn't start using the well water level changes till 1980, but they did have general diversion data, probably not as tight as it is now, but he was able to go through, look at weather, look at evapotranspiration is calculated instead of looking at it from space like we do now, and then looking at these diversions and returns. And so it may be a little less fine grained, but yeah, that's how they did it. They did have water budget data.
Okay, thank you. Any other questions? Okay. All right.
Okay, thank you very much.
Okay, Mr. Chairman, we'll move on to the next presentation from Ethan Geisler.
Okay, thank you, Ethan.
No, you can't do that. No.
Right. Yeah. Thanks for having me. So my name's Ethan Geisler. I'm a Technical Service Bureau Chief here with the Department of Water Resources, and I'm going to talk about Eastern Snake Plain Aquifer discharge. So Mike oriented us pretty well to the ESPA model boundary. I'm going to focus on two areas today, two reaches that have aquifer discharge. So the first one is the near Blackfoot to Minidoka reach, and the second one is the Thousand Springs reach, which I'll focus on first here. And so in the Thousand Springs reach, that Milner to King Hill reach, the Snake River actually incises into the basalt flows there. And that actually intersects with the water table at various locations. So this graphic is showing that intersection at the river surface, but it can also happen along the canyon wall. And so I'll show some examples here. And at times that can be easy to measure. So such as this spring that's coming out of Thousand Springs, channelized, has road access. You could get a measurement device in there pretty easily. But there are a lot of other springs that are like this that come off the canyon walls, spread out over the wall and the vegetation there, and are just impossible to measure directly and to monitor. And you also have, like that graphic showed, seepage that comes in either at the side of the river or under the river as underflow. And it's just really hard to differentiate between what's the Snake River and what's that spring flow. And so to really get a good estimate of discharge out of this Thousand Springs reach, the USGS developed a method back in 1995. So I'm going to zoom into these springs here a little bit more. And basically we're taking these 17 springs. The USGS takes actual measurements in the March and April time period at these sites. So you can get a above and below stream sometimes and get a pretty good estimate of that spring flow from that reach. And you're applying statistics over that for the entire water year. So for the 2026 water year, we're taking 2026 spring measurements, and you can get at a pretty good projection of what the 2026 Thousand Springs discharge is going to be. And so that's the plot here that Mike kind of showed in his presentations. We have cumulative storage change here on the left axis, Thousand Springs aquifer discharge here on the right axis, and then the years on the X. And so you can see from 2025 to this 2026 projection value, those flows are projected to go down. And so that aligns pretty well with the aquifer storage change as well. And so I think the big takeaway from this graph is that aquifer discharge and aquifer storage change are pretty well correlated, especially in that Thousand Springs reach. You can see discharge follows right along with how the aquifer is behaving. And so this has implications many of you are aware of that happened this year. So the Snake River near Murphy Gauge is just downstream, and a lot of these Thousand Springs discharges actually feed into that flow, especially in the low flow period. And so this is the AADF graph that the department runs. I'll kind of walk folks through this if you're not familiar. So on the y-axis here, we have CFS for all of the data sets, and then it's on a calendar year. And we take the Snake River near Murphy minimum and median of record here in the red and green. We plot that along with the 2026 value, which is that blue line. So the actual USGS data is the blue. We also have the Milner flows here just for reference, so we know what's coming into the system a little bit. And so this AADF is a pretty good proxy because we're trying to take out Idaho power operations and those Milner flows. And so it's a pretty good proxy for what we're seeing in the Thousand Springs reach. We did have a shortfall here in the March time period that went below our minimum, the board's minimum flow water rate of 5,600 CFS. I'm not going to focus on that too much. I really want to point out this June and July time period where it's 3,900 CFS is the minimum. You can see here those AADF flows got pretty close to the minimum, but didn't drop below. And so that's just another kind of piece of context for these values are lower than we've seen the minimum of record in the past, but not quite to that 3,900 CFS minimum water rate. And so I'll kind of increasing on that a little bit. I'm going to go through each of the springs that kind of feed in that both the Department of Water Resources and the USGS monitor continuously. So these are the springs that are easier to kind of measure over the entire year, and we have instrumentation in them. And so the first one here, I'm going to move downstream to upstream. The first one here is Kern Tunnel. We zoom into this one. This is just a bar chart of the total discharge over the year, over the water year. And so you can see kind of the progression over time, similar to what we see in the aquifer storage change plot that Mike just showed. But I'm mainly going to focus on this right portion for all of these bar charts. And I think I've told this story in the past. We saw that increase from 2017 at or around 2017 onward to about 2020, 2021, where we saw a decrease. And then since then, it's been kind of mixed results of either a slight increase or maybe flatlining a little bit. So I'll go through each of those. We look at the CPAC sites. These are sites that Department of Water Resources monitors. I'm actually going to stack these on top of each other because the trend is pretty similar. And I'm mainly just going to focus on 2025 was a little bit higher than 2024 in both of these sites. If we move on to Box Canyon, similar narrative here, 2025 a little bit higher than 2024. And for this one, I've actually plotted the daily time series here. So on this plot, the gray range here is the period of record. So in this case, it's from 1990 to 2025. The darker dashed line is the median of that period of record. The gray solid line is going to be 2025, and then 2026 is this black line. And the main takeaway from this graph is just to kind of illustrate a little bit where 2026 falls in line with 2025, I think is the best purpose of this plot. And so you can see here, this is on a water year basis. So early October 2026 was a little bit above those 2025 values. But then as we went into that pretty dry winter and into the summer, those values decreased and deviated from that 2025 line quite a bit. So I would expect that 2026 bar on the bar chart to be slightly lower than the 2025 value, but we'll see how the rest of the month and a half plays out here to end the water year. If we move on to Briggs Springs here, this is a USGS site. Maybe a slight decrease when comparing 2025 to 2024. And we see a similar trend when we're looking at 2026 compared to 2025 for the continuously monitored data. If we look at Blue Lakes, slight uptick from 25 to 2024. And you can see here, this one's a little bit different than the other ones. It actually matched 2026 matched 2025 pretty closely until that April-May time period where it deviated quite a bit more. And so I would expect that 26 value to be slightly below 25 just based on that. And then the last spring here, Devil's Wash Bowl, this is a USGS site, slight uptick from 24 to 2025. And then looks like decreasing in 2026 compared to that 2025 value for most of the days. And so I wanted to see how all these added up, just the continuous sites that both the department and the USGS monitor, see if there's a trend that comes out of any of those when you kind of add them all up for that bar chart and the continuous sites. So this is all of that data that I just showed, but just stacked with the exception of the CPAC sites, and I'll show those in the next slide here. But basically just to take away from that trend, 2025 is higher than 2024 when you add those all together because they are different magnitudes. Box Canyon's a big portion of that. Kern Tunnel's a very tiny piece. So, and then if you add the CPAC sites on, we only have data back through 2011, so I didn't want to throw your eyes off with any trends. So I'll kind of flip back and forth between those. But you can see that trend still holds from 24 to 25. And then if we look at the continuously monitored data, so this is all of those sites added up on a daily time step. You can see the trend that kind of comes out there. Maybe not as drastic as in some of those previous continuous plots that I showed, but 2026 is below 2025. So I would expect it to drop below. And this is kind of the same narrative that we saw with the Kellstrom and Mike's storage change calculation, where 2026 is looking like it's going to be below 2025. And we have a couple data sets that kind of show that. So I'll stop there for a second on the Thousand Springs Reach. If there's any questions on these or these springs or the Thousand Springs Reach before I move into the near Blackfoot to Minidoka discharge.
Mr. Chairman, Ethan, this is Brian O. Bad Brian or okay. So can you go back to that the Murphy gauge that shows the big jump here just recently?
There we go.
Yeah. So that's including the Idaho Power water and our Water Resource Board water that ran, right? Or that
Yeah,
blue line is not. So
the blue line include. Yeah, so the blue line is the Snake River near Murphy gauge with no corrections. And then the black line is going to be the AADF excluding all Milner flows.
Right. So we've had a pretty big jump here recently. Is that the Bruno or is there some other thing that's really jumped?
Yeah. So as you can see here, the minimum of record, we tend to increase here in that August time period. And I've looked back at that in the past, and a lot of that is increase in return flows, as well
Yeah.
as just a decrease in consumptive demand from Water District 2. They kind of peak out in their consumptive use in that July time period, and then it starts to taper off in that August time period. So I think that's what you're kind of seeing here, are those
Okay.
two pieces come back into the river reach.
Okay, thank you.
Yep.
Any other questions from committee members or board members?
Yeah, Mr. Chairman.
Yes. Go ahead now.
Ethan, what's the explanation for the July 1st significant bump in the Swan Falls graph?
Yeah, that's a good question. We were tracking that Swan Falls flow pretty closely around that time because we were pretty close to that 3,900 minimum. And you can see here, there's a pretty big bump, and that was a well-timed rain event. I think we got some monsoon moisture throughout that southern Idaho region, which increased return flows and tributary flows, and then also decreased at the same time that consumptive demand out of O2. A lot of folks turned down their canals or turned their pumps down. And so that is the reason for that increase there in July.
Thank you.
So Ethan, this is Dean. I have a question. If you could go to your Blue Lakes, the slide on the Blue Lakes Spring.
Yep. This one or the next one?
The one that shows the line on the annual one there. Okay, yeah, that one right there. So this line's taken a pretty substantial drop. Is this flow calculated? I mean, because that's a pretty fast drop. Is this flow calculated before or after the City of Twin Falls diversions?
I think it includes, it's an aggregate of a couple monitoring sites. And so I believe it includes that location, but so I think it's after, but we include that data in this value.
Okay.
If that makes sense.
Okay. So it doesn't, so the City of Twin Falls diversions are calculated as, the reach gains in that spring are, before Twin Falls takes their water out. Is that right?
Correct. Yes, I believe so.
Okay. I know, because it's kind of difficult to pick that up because you pick water up in Alpheus Creek too as it goes down. So, all right.
Mm-hmm.
That was
Yep.
the question I had. So thanks.
Okay. Yep. Okay. Any other questions here? I'll move on to near Blackfoot to Minidoka. So just orienting ourselves here at the ESPA model boundary. I'm going to focus in on this near Blackfoot to Minidoka reach. We zoom in here, and many of you are familiar with this being called the near Blackfoot to Minidoka reach gains. For this talk, I'm going to call it the Aquifer discharge, just to differentiate it from the water right accounting reach gains. And so this aquifer discharge basically is the gain or loss of water between the beginning and end of a river reach. And we're trying to isolate what's coming from the aquifer, both for aquifer metric, as well as we use this calculation in the ESPA model as well to calibrate to. And so basically it's the outflow minus the inflow. So that near Blackfoot to Minidoka gauge minus the Snake River near Minidoka gauge minus the near Blackfoot gauge. We take into account reservoir change in content and evaporation at American Falls and above Minidoka here, as well as add back in diversions. And then this is where it starts to differentiate from the water right accounting reach gains. We actually subtract out return flows. And so in this reach, it's the Fort Hall canals, People's Canal, and then the department actually monitors the Aberdeen Springfield returns. And then we're taking out major tributary flows. So in this case, it's Portneuf and Rock Creek. And so we can calculate that on a daily time or on a monthly time step and add that up over the year. And you get an annual value here that is similar to what we see. These bar charts are similar to what we see with the Thousand Springs discharge. And if we overlay, so this is just the 2025 value, I should say, for the water year. We don't project out into 2026 just because we don't have that type of analysis. And then here, if we overlay the cumulative storage change plot that Mike shows on top of that. You can see that tracks pretty well, especially later in that period of record to the aquifer storage change. And if we convert that to CFS, you see similar trends. I usually present this in water year, but I know there's a lot of discussion on the calendar year for this calculation. It's in the amended final order approving the stipulated mitigation plan between the groundwater districts and the Surface Water Coalition. There's a reference in there to these near Blackfoot to Minidoka reach gains on a calendar year basis. And so I've plotted those up here. So this is still the water year in green bars, but whenever you plot this red line, that's the calendar year. So from January through December. And you can see that there is some variability, some differences, but overall that trend remains the same as you go along in the years. And I did mention we calculated this on a monthly time step. And so I don't have 2026 data finalized for you, but I wanted to give you kind of some insight into what we're seeing so far. And so this is the way I've kind of shown it. So we have monthly data that we can add up over the year. And so I plotted this in that kind of range of data. So the 1980 to 2024 range is here in gray. The median of that range is this dashed line. We have 2025's value in this gray, so we can see where it's kind of falling over the year. And then 2023, I think, is referenced in that stipulated mitigation plan as a threshold. So I plotted that in red here because I think there's some additional management activities that occur once you get below that value. And then if we plot 2026 on top of this, you can see where it falls. So you can see it falls both below 2025 and 2023 for whenever we calculate that data through July. And it's kind of riding along that lower percentile. I think that was the year 2022. And so it may fall at that point or around 2025. It remains to be seen if this goes. You see those lines don't change trajectory a whole lot historically. And so, but it remains to be seen where that kind of falls out. So these endpoints here are kind of what's plotted on that bar chart that I just showed. And so kind of the final slide here, I wanted to combine all of those together, all the data sets that we have. So on the left axis here, we have that ESPA storage change plot, both in the top and the bottom. So that's Mike's plot that he showed previously. And then on the top here in the green bars, we have the near Blackfoot to Minidoka discharge. And then on the bottom here, we have the Thousand Springs discharge. And it kind of just shows you that those are pretty well correlated. The ESPA leaks, like Mike has said in the past, and it's leaking in these reaches. And so gives you an idea of where we're going to fall in 2026. I think a decent projection here is somewhere in between this range of what we saw in 2025 and maybe that lower minimum in 2022. Kind of remains to be seen. But overall, I think the major takeaway from this is most data sets are showing that 2026 is lower than 2025. And so let's hope for some good winter snowpack and a change in course here next year. So with that, I will take any questions you guys have on any of the discussion we've had so far today.
Any questions from committee or board members?
Mr. Chairman, Ethan, this is Brian O. Ethan, I know we're going to at some point in the near future replace the at Blackfoot gauge, and I've thought for years that you know that's really the reach between at Blackfoot and near Blackfoot is a gaining reach, and that should be noted, you know, mainly because we're targeting recharge in the Blackfoot area. And some of that recharge is going to come into that next reach theoretically or hopefully. And it would be nice if we could, you know, to me, that's where the accounting really changes between Upper Valley and Lower Valley. And so whenever that at Blackfoot gauge is made more accurate, replaced, I think we need to know that reach gain between at Blackfoot and near Blackfoot. It has been a gaining reach this year generally, and a lot of years it was not, and that was gauge inaccuracy, at least in my opinions. Just a comment there. Thank you. Nice information.
Yeah, Mr. Chairman, Mr. Olmstead, yeah, I do have one comment there. So I have looked at that, and I think you mentioned to and alluded to a little bit, it is a decreasing reach gain at some years. And so we'll continue to look at that. We have some of that data already pulled together. And so I'll keep looking at that and see once that gets incorporated.
Follow up, particularly our new recharge sites, I think will target that reach pretty effectively. It's really the first gaining reach. I mean, we have, really losing reaches for a long ways above that. And so I think it's important to just keep track of how our recharge is helping. Thanks.
Okay. Yep.
Any other questions or comments from
Mr. Chairman, this is Jeff. Back to that slide that had the graph on it that showed the reach gains and the 2026 was in, the one that showed 2020. Yeah. Have we done any math to calculate what that is in acre feet? Or can we do that once the irrigation season's completed?
Yeah, when you say calculate an acre feet, the current difference or?
Yeah, well, the difference between, I guess, from 2023 to 2026, because that's what
Yes.
the settlement agreement references. Sorry.
Yep. No, yeah, I could calculate that and get it to you folks. Yep, that's
Okay.
not a problem.
That'd be great. Thank you.
Any other questions or comments? So Ethan, could you go back to the one, the last slide you had up there with both the Hagerman Reach and the Blackfoot Reach? Yeah, there we go. So we're about 70% or better of the outflows of the aquifer are coming out of Hagerman. Is that the way I see that probably? Versus
when you convert it to CFS, I think that Thousand Springs reach, that annual value comes out to be quite a bit higher than the near Blackfoot to Minidoka. They're on different scales. They're on the right axis. You're right.
Okay. Well, I think that just goes to a point that the Thousand Springs is, it's going to take its water. It's 70% or better of what the whole outflows of the aquifer, are there. So that's, as we go forward, I think that's a challenge we have in trying to increase the reach gains in the upper part of it. So anyway, any other comments or you have more of your presentation, or are we about there?
Nope. That's it. Yep. That's all I have for today.
And any other questions or comments? Okay.
Next presentation will be from Alex Moody here at
All right.
at IDWR.
I think we have
And he excuse me. Okay, Alex Moody will make the next presentation at IDW here, and his presentation is on parsing out the different aquifer management measures to determine their impact on the aquifer.
Second, we get set up here. I think and I have the link, so I should be able to. It should be in.
You should be able to share.
Okay, thank you. All
All right, good morning, Mr. Chairman and members of the board. My name is Alex Moody. I'm a groundwater modeler in the hydrology section here. And I'll be sharing some modeling results about managed aquifer recharge impacts. So we use our Eastern Snake Plain Aquifer model version 2.2 to look at these impacts. I run different scenarios for water resource board recharge, groundwater district and city recharge and mitigation. That's part of the settlement agreement, as well as separating out pumping reductions from groundwater districts. So I run 3 different scenarios and look at the impacts of these to aquifer storage and aquifer discharge. On the right, there is a table just summarizing for the calendar year how many thousands of acre feet that go into the model, just to give you a sense of what we're looking at and how we parse it out for each scenario. On the right, there's that 5-year moving average. And then this year for board recharge 2025, we have 133,000 acre feet, and then into 2026, 52,000 acre feet. These scenarios have different, we know more about board recharge and pumping reductions than sometimes we do with the groundwater district recharge, but we do the best we can to locate that recharge and put it in the right month. Zooming into just recharge since January 2025 to give you a sense of the timing. For all graphs in this presentation, board recharge will be in the black line, groundwater district and city recharge will be in kind of the purple line, and the orange line will be pumping reductions. So all these activities complement one another pretty well. Board recharges in the shoulder season, and then the pumping reductions obviously happen during the irrigation season. How this looks across the plain and within the ESPAM 2.2 boundary for August 2025 to July 2026. The darker blue is going to be where we're having more recharge. You'll notice the scale is in logarithmic scale. So we have a lot going on in the lower valley. This more diffuse lower value is settlement agreement activities. And then pumping reductions across the plain. If you have a negative pumping reduction, that just indicates that pumping exceeded baseline conditions. But we have that spread across the plain, a lot more widespread than the recharge. So the model period, in this case, we run it through July 2026, and this is a monthly time step from January 2014 to last month. A quick overview of model results. This plot shows up top just recharge for the period of record for each activity. The second and third plot are aquifer reach gains for above Milner and below Milner. I will zoom into those here in a second. And this bottom one is cumulative storage change due to all recharge and mitigation activities. So focusing on storage results, trying to line up with Mike's storage change calculations, I pulled out just April cumulative storage change for each scenario, as well as totaling them all up in this gray line. So you can see with these percentage, what they're representing is change from year to year in this cumulative storage change. So in 2026, we're down about 2% in total storage change from all activities. Same in board pumping reductions. That change actually went up about 2%, and then groundwater district and city recharge, there's been about 14% change in cumulative storage change. What those look like in acre feet, we are 1.52, we've added 1.52 million acre feet to date. remains in storage due to board activities. 330,000 million acre feet, or sorry, 330,000 acre feet from groundwater district and city activities, and then pumping reductions were at 1 million acre feet. I change this plot around every year, but I'm just trying to get at storage retention. So if you look at all water that's been put into the aquifer to date, and compare to that to what remains in the aquifer, that's going to give you this percentage that I'm presenting here. So these plots, the board dotted lines are cumulative recharge, so we're up pretty high. And then this black line is what remains in aquifer storage. That'd be that 1.5 million acre feet number, and so on for the groundwater district and city activities and pumping reductions. In terms of percentages, that's 53% of board recharge remains in aquifer storage, 25%. Sorry, I didn't change that one. Groundwater district and city recharge is at 25%, and then pumping reductions about 47% remains in aquifer storage. I'm going to put this in the context of this aquifer storage change that Mike has calculated. So we saw this plot in Mike's and Ethan's presentations. And then what we're doing here at the end is I'm subtracting out the modeled results of storage change from the observed storage change to give a sense of where we might be without all aquifer mitigation. And to my eyes, I feel like I can say we're definitely moderating the decline a bit there. We would potentially be below the 1912 storage change volume were it not for aquifer recharge. Zooming in here to give a sense of what impact each activity is happening. Zooming into that same plot from 2010 on. The black line is again the observed cumulative storage change. The dotted line is all of the activities subtracted out from that, the dashed line, and then the dotted lines are each activity subtracted from observed, showing kind of the relative impacts of each, how they look in the cumulative storage change, and then the total. So this gap here between the black line and the dashed line, that's about 2.8 million acre feet difference. All right, moving on. Well, I'll stop there. If there's any questions before moving to aquifer discharge. All right. Looking at reach gain, these are the same as Ethan's aquifer discharge values. We're just looking at groundwater discharge to the river. Impacts above near Blackfoot. The graph shows both an acre feet per month and CFS, what those look like on a monthly time step. So all activities are impacting that reach, even early on when board recharge was mainly occurring in the lower valley. You can see there are some small impacts. And this table here summarizes the seasonal impacts in acre feet, thousands of acre feet. So April through October during the irrigation season, all activities are having about 88.4 thousand acre feet impact to the above near Blackfoot reach. Near Blackfoot to Minidoka, total we have about 53.6 thousand acre feet impact with all activities during the irrigation season. And from this graph, I really like to point out how this board recharge impact is just slowly growing since the start of the model run and continues to grow steadily. And then below Milner, this is the Thousand Springs reach. Board recharge definitely shines here. We're adding above about 105 CFS on average to that reach. Total impacts 58,000 acre feet, and board alone is about 44,000 acre feet during the irrigation season. So if we look at this in terms of a proportion of where impacts occur, and we split it out by activity, I think we see some interesting things. We could all see in those previous plots that there are differing volume amounts and rate amounts for each activity. But when you look at the proportion of each activity, I think that can tell you some interesting things about how that's changing through time. This is the one exception. The brown color here is, well, this is per reaches. So the brown here is below Milner. The blue is near Blackfoot to Minidoka, and the black is above near Blackfoot. So this past year, board recharge had about a 40-60 split above and below Milner. So we're definitely impacting below Milner reach gains more with board recharge, but there is a fair amount of above Milner impacts. And on, again, just driving home, all mitigation impacts all reaches of Snake River, but they each have different and unique signatures based on their location and the distance to the river. So you can see groundwater districts and city mitigation is mainly impacting the reaches above Milner, but there is a small impact below, and that's kind of remained roughly constant throughout the period that is shown here, whereas board recharge can really vary based on the year. So if there's any questions on the reach gains, I can answer some now or move on to the movies.
Any questions from anybody?
Dean, this is Jeff. This graph we're looking at right now isn't measured volumetrically. It's just percent wise. I think, is that correct?
Correct, Mr. Raybould.
Yeah, because even though in 2017, 2018, it looks like there was more recharge that benefited above Blackfoot, volume wise, there was probably still more recharge done in the lower valley than the upper valley.
Correct.
Okay, thank you.
All right, any other questions? Okay. Let's see the movie.
Okay, for to help save a little time, I'm gonna focus on the board recharge and for the modeled movies, and then look at comparing that against what we actually measured. So this legend on the right shows modeled impacts to aquifer heads, about 2-foot intervals. So the blue greens are going to be positive impacts, which is pretty much all we're going to see here. This runs from 2014 to present day. You can see most of the recharge is occurring in the lower valley. We do have some upper valley recharge. It doesn't necessarily always persist as long because it quickly gains to the river. But we have this front kind of slowly creeping up into the upper valley, which is why we saw that slight increase or that gradual increase in modeled aquifer gains in the near Blackfoot to Minidoka reach. Sorry. And then if we look at this in terms of how it compares to observed water level changes. So this uses all our transducer data to make an interpolation similar to what Mike does. I don't filter out wells like he does, but so I interpolate those values and then I look at those relative to the modeled water levels and use that to try to say something about what's causing that water level change. So you'll see this ternary color bar that helps to visualize that. Something that's light blue is going to be mainly due to board recharge. The more pink colors are going to be from groundwater district and city conservation. So that's all mitigation, all pumping reductions, all recharge from those parties. And then the yellow would be other sources, which could be incidental recharge that is not modeled, or natural recharge that is also not modeled. I tried to speed this one up this year. Hopefully it's not too fast. The contours show the observed water level change. So these blue contours are a positive water level change, and then brown contours are negative. You can see the blues in the lower valley popping up because of board recharge. Pumping reductions are causing a lot of these, the pinks in the upper valley. And you can really see how dynamic this system is. This is kind of filling in the gaps between Mike's storage change contours, though definitely not as rigorous. But I think it helps illustrate, we are having an impact in water levels. And just a quick summary, board recharge has increased aquifer storage by about 1.5 million acre feet. All told, with all activities, we've increased storage by 2 million acre feet. Irrigation season reach gains, we are impacting that by about 54,000 acre feet in the near Blackfoot to Minidoka reach, and below Milner. Gains for the past 5 years on average are about 143 CFS during the irrigation season. And kind of emphasizing Mike's, this is a leaky aquifer point, share of each year's application returns to the river within the year, and the remainder can persist in storage for a long time. And that is all I have, and I'll stand for any questions.
Any questions from committee or board members? Okay, thank you.
Thank you.
Okay, Mr. Chairman, next we'll have an update from Brian Reagan on the Water Management Information System Database Migration and Enhancement Project. This is the monthly time step database for the groundwater pumping data. So I'll let Brian give his update on this effort.
Sure, I'm going to be sharing my screen here. Let me get the presentation up and running. Can you see my title slide?
Yes.
Thank you. Well, good morning. My name is Brian Reagan. I work in the Water Administration Bureau. Appreciate the opportunity to present to you. I am the project manager. And over the next 15 minutes, I'll give you an update on the WMIS database migration and enhancement project. A project description: we propose to migrate the Water Measurement Information System, or WMIS, database into the Water Information System KISTERS, or WISKI database. Both these databases are currently used by the department. We also would like to enhance the WMIS functionality and improve access to the data. Why is this necessary? Currently, WMIS cannot store more than one single diversion volume amount per year, so we can't handle monthly data. What is the catalyst? Well, the 2024 settlement agreement between the Surface Water Coalition and the groundwater districts in their mitigation plan required that starting this year, they begin to report monthly irrigation diversion volume, so June through October. We had identified other enhancements, such as being able to hyperlink to back files through this new database. We have a number of field notes, photographs, variants and extension paperwork, other documents that we would like to be able to get to through this database, but we currently cannot. Similar to how our water rights back file database works. We also would like to have a data importer to automatically load data into the database. Historically, this has been done manually, and over the last number of years, we've used some other software to do that automatically, but we've experienced some trouble with that software. So as part of this enhancement, we would like a data importer. We also would like a data exporter to get data out of the database. Currently, it's not entirely user-friendly to get data out of the WHMIS database. We do have a public-facing map with the data that citizens of Idaho can get data out, but those staff internal to the department, we can use Microsoft Access to actually go into the database itself and query any kind of data that we want out of the database. And we do that often for consultants and water districts and groundwater districts. And we do that through these standardized reports internally. So we would like the public to also have the ability to extract data easily and in a standardized form. So the WHMIS database, it is a relational database. It's been used since approximately 2007. We have over 10,000 records in there currently. It primarily is used for groundwater diversions. And we track well location, annual diversion volumes, the measurement method, any measuring devices that might be there, the owner and operator. So sometimes the water right associated with that well, or excuse me, the water right owner associated with that well is different than the operator. So we can track those two different contacts and other site characteristics. WHMIS is linked to our water right database. So when a user goes into the database, they can see the water rights associated with that well. And this data is served to the public via an online map. The WSKI database, another relational database used since 2019. There's over 30,000 stations in this database. It does track groundwater and surface water data. So well location and construction, groundwater levels, there's surface water and groundwater quality in there. Who's collecting the data? How are they collecting the data? Again, other site characteristics. This database is very robust. It can handle the amount of data that we are proposing to incorporate into it, and there is room for expansion. In fact, much of the data that you have seen in the previous 3 presentations was taken from the WSKI database. When the department realized that we needed to upgrade the database, we had several options that we considered. One was to do nothing and just track the monthly data from the groundwater districts, outside of the database and spreadsheets. We thought about rewriting WHMIS using Idaho Office of Information Technology staff. We looked into going out to open bidding from other software developers, or merge the WHMIS database into the WSKI database. And ultimately, that was the option that was chosen. So Kisters, they are the company who wrote the WSKI software. So why did we choose them? Well, they were a known entity. We were already in contract with them because we use WSKI. They're familiar with the database, and WSKI could do what we needed. Additionally, Idaho IT staff, they weren't able to allocate the resources to this project. They just didn't have the human resources and the time to do this. It would have negatively affected the prioritization that we have with IT. So throwing this big project in would really negatively affect that roadmap that we have with IT. And lastly, the IT department, they actually advocate for state agencies to utilize third-party off-the-shelf software. So who are the parties involved in this project? So we have the Water Resource Board. They are the funding source, and I want to thank you for the generosity in that funding. The Department of Water Resources, we are the customer. We host the databases. Idaho IT, they provide us the technology support and any security concerns. Kisters, they are the contractor. And then SHI International, they are a third-party subject matter expert. And what their role is, they're helping the state agency coordinate the project with the contractor. A lot of the information is run through SHI, and so they are really there to make sure that the department gets the end product that they want. Okay, budget. The budget came from an executive, followed from an executive order, the Protecting Idaho Water Sovereignty Act. So the board allocated $1 million to this project. 500,000 of that was allocated in November of last year. The other 500,000 was allocated in May of this year. So here at the bottom, we can see the total project budget, the expenditure. So to date, we've spent $217,000 plus dollars. That went to an inception report, which I'll talk about here in a moment, and then the purchase of a server, which I'll touch on later. The inception report, what that was, when we approached Kisters, we provided them copies of the WHMIS, WSKI, and our water right database so that they could pick those databases apart, determine how to reassemble them, and provide a response to the department on what their project plan was and the estimated costs. So the remaining available is $782,000. So this table at the top shows just the estimated database cost, and this does come from the inception report from Kisters. So we have the line items, we have labor, licensing, and annual support. We have the Kisters charges, and then the SHI charges. What you see here in parentheses, I've added in a 50% contingency on labor, just to account for that in that eventuality. So you can add these totals vertically or horizontally. SHI, they have varying percentage rates in terms of what they charge for their services, and those are built into these numbers. So this is just the database cost here. So between $431,000 and $600,000 for the database. The table at the bottom shows the total project costs. So I carry those numbers down to the database. We did have to purchase a server. You may be familiar with that. IT made us aware that they just didn't have the capacity for this project. So a server was necessary. And then we have the $10,000 for the inception report. So the total project should range from about $650,000 to $820,000. Project status, there were a number of steps involved. We've completed some, we are finalizing another, and we still have a lot of work to do. Where we are currently is finalizing the statement of work document. And what that is, it's kind of a high level document, but with some detail in it that outlines the responsibilities of Kisters, the Department of Water Resources, and IT. And this document was very important because ultimately it will help us end up with a product that works for everybody. But their IT had some, they are managing security, and so because we have users of this database who are outside the department, there were a number of security concerns to address. There's statutorily required security protocols that need to be in place, and also once this project goes live, the IT department, they have some maintenance that they'll do on this on the back end of it, and so they really wanted to lay out what all their requirements were going to be. This table here, we've had a number of meetings with all the parties. There's been various documents and database submissions back and forth, and then we have the 2 board resolutions. I do want to point out on the software development side, this agile development, what that means is as Kisters is creating the database, about every 2 or 3 weeks, they will send us a product to test. Rather than waiting months till we receive something, every few weeks we will see their progress and be able to test it. and we will be able to tell them, hey, this is working great, do more of that. Or this really isn't what we had in mind. It's not really working. Can we change this over here? So that agile development will be crucial for the end result of this project. We did have some challenges affecting the timeline. There are regulations over how state agencies can go out and get contractors. So there was a lot of discussion about going out to bid. Once we identified we wanted to go with Kisters, so how do we do that? Do we have to go out to bid or not? And that's where SHI really came into play, since there already were contracts with SHI and Kisters. We were able to go right to Kisters for this project, so we did not need to go out to bid. There was time spent on the inception document preparation. It took a little while to get them copies of the databases. Took Kisters a little while to generate that document, and then there were a number of meetings, questions generated from that document. IT, they had existing priorities ahead of them. They had already projects on their plate that they needed to complete before they can even spend any time on this project. I mentioned the server. They told us that they didn't have the capacity, the storage space, or the processing power to host the 3 different environments for software projects such as this. So there's a development environment where the project is being developed. There's a staging where it's like, okay, we're getting ready to go to production. So all those 3 different environments, they do take memory and space, and IT just didn't have it. IT being a state agency, they were affected by the budget holdbacks this year, and so they didn't have the budget to purchase the server. And again, so that's where the Water Resource Board stepped in so generously for funding. The hardware, the server has been purchased. It is going to be arriving in October. There was a 3-month lag time in purchase till we receive it. Once that gets in, IT will get that server up and running, and at that point, Kisters will be able to access that server and actually start the work of programming. And last comment on the statement of work, I mentioned it before, but this is the first time IT was using this document. And so, there were some growing pains as we worked through the content of that document with all 3 parties involved. So it has taken some time to get to this point. Last slide here. So what's the estimated time frame to have a functional database? Summer of 27 is when we'll have a functional database. It likely won't be fully complete and done at that point, but what we will have is the ability to enter data into that database by departmental staff. Likely what will follow are the public facing, the web applications, data entry by non-departmental staff. There are a number of water districts and groundwater districts who have water masters and staff that aren't departmental staff. And so they're trying to get data from on one side of the secure firewall into the database. That will take some time. So what are we doing with the data between now and then? Well, the WMIS database, it's still functional, still supported, and we're still using that. The groundwater district monthly data, currently we're tracking that in spreadsheets, and Microsoft Access is available to us. And that data will be made available upon request if needed. And that's the end of my presentation. I'll stand for any questions. Thank you.
Mr. Chairman, Brian, this is Brian O.
Go ahead, Brian.
So Brian, this is going to be great information. Looks challenging. So if I want to see the monthly diversion reports, I can request those. Is that? But they're not ready to go on the online yet.
Yeah, currently we do not have a data, Mr. Chairman, Mr. Olmstead, we currently don't have a database that can hold that monthly data. The way that the settlement agreement speaks is that data will be submitted to the water masters, and then that data will be made available upon request. And so we have the data, it's ready. We just haven't had a request yet. So we're ready for those when they come in.
Okay, so I wouldn't request you, then I would request to Water District 1, for instance, or?
Well, it would be, water district, 130 in southern Idaho, 100, 110, 120 in eastern, not through water.
Okay,
You could ask me directly if you would like.
that'd be great. Thank you very much.
Any more questions from committee or board members?
Mr. Chairman, if I may, Brian, does the old WMIS, is the idea to take the old WMIS data and have the new whiskey's software be able to access all of that? And since the old WMIS data was only annual, we're not going to have monthly prior to the time that the whiskey is updated. Do I understand that right?
Mr. Chairman, Mr. Barker, all of the existing data that's in the WMIS database will be migrated into the whiskey database. So up till the end of 2025, that is just annual data. We are collecting monthly data as we speak. And once the whiskey database is prepared for that, we will be able to start loading the 2026 monthly data into the database. So there will be a, let's say, 2025, 2026 dividing line between when there is annual data available versus, annual and monthly data available. I may add that at the end of this, WMIS is going away. WMIS will be decommissioned and taken offline.
And so this will include all of the basins, like, for example, 37 will be part of this new whiskey database.
Mr. Chairman, Mr. Barker, yes, everything that is currently in WMIS now, and as the department expands and creates new water districts and new records are necessary, all of that additional information will go into the new database as well.
Thank you.
You're welcome.
Any other questions? All right. I think, is that the last one, Brian, that we have?
That's the last presentation. You're down to other items, Mr. Chairman.
Okay, do we have any other items from any committee members?
No, Mr. Chairman.
Okay, Brian or Pat, anything?
Nothing here, Mr. Chairman.
Okay,
I'm good. I'm good, Dean. This is Brian O.
okay, I guess we'll.
Mr.
Go
Mr.
ahead,
Chairman,
Brian.
you do have Director Weaver present on Zoom. Just may want to ask if he has anything to discuss.
Okay, Mr. Director, do you have anything you'd like to discuss?
He must not have anything to discuss, Mr. Chairman.
Okay. All right. I guess we're just looking for a motion to adjourn. Is that where we're at, Brian?
Yes, we are.
Okay.
So moved, Mr. Chairman. Brian O. moves. We adjourn.
Okay, do I have a second?
McMahon for the second.
Okay. All in favor, say aye.
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 We're done. Thank you very much for,
Thank you all.
and we appreciate all the work the presenters put in for this committee meeting today. So thank you.
Lots of good information. Thank you.